Recording is rolling. It is Friday, March 6th. So I know originally we were going to test bridges today, but yeah, about a third of the class is gone. So we're going to postpone that until Monday. Instead, I figure it's probably a good day to get the ball rolling on thermodynamics. So I have some posters and demos lined up for you guys. And then, okay, yeah, we'll do testing toothpick bridges on Monday. Okay, before we get to all that class stuff, though, some other things. Electives. So I got an email recently. It says about this new procedure. Remember, this is all new. This is different than they've done it in past years. Okay, so here's the email text. So we're all looking at the same thing here. We all have the same knowledge. Students now have the ability to select their elective options. I think this just opened in the last 24 hours. So, guys, if you go to focus, here, I'll tell you guys how to navigate there, just verbally. If you go to the top right corner of focus, there's a drop-down box to select the year. You want to select next year, which is 2026, 2027. Okay? You guys got that? Okay, so I'll say it again. In your focus on the top right, now your focus is different than my focus, but on the top right, there's a drop-down box for 2026, 2027. So first select that. And then if you look on the left side, there's a bunch of tabs, and I forget exactly how it's phrased, but I think one says something like select class or class request or something like that. Okay. And then in there you can select elective options. Now, some of my math students were showing me that your core classes may have been filled in already by your counselors. So I have Algebra 2 classes, and their next class is pre-calculus, so that's already been filled in by their counselors. But they need you guys to select some electives. They want you guys to select 5 electives. 5 electives. Can you guys do that? Select 5 electives. You guys write that in your planner to select 5 electives. All right, so 5 electives. All right, and then pretty soon, it looks like in a couple of weeks. It looks like okay, the week before spring break. The week before spring break, and it's probably take a few days here because they need to talk to everybody in the school. Your counselor is going to meet with you guys in your English classes to discuss the course you guys are taking. All right. So, any questions about scheduling? About that? All right. So there we go. All right, we got that. Point. All right, and then last detail here before physics is what are you guys going to do with your clocks this weekend?
You gotta push it forward.
Yeah, it's going to spring forward. So 7 o'clock becomes 8 o'clock. That means we're all going to lose an hour's sleep. Or yeah, it's that one. It's that one. Now spring ahead. All right, so daylight saving. All right. All right, you guys got that? Yeah, thank you.
I think it's not daylight saving for now.
Or is what?
I think it's not daylight saving.
Not that I've heard of. Yeah, I know it's kind of a political issue that comes up here and there. But I think, if I remember right, I think back in the 1970s they reverted to not doing it. But then it's like, like everybody was wants something different.
Yeah.
Yeah, there's like a whole history behind it, but I guess we got what we got, right?
But then they
Yeah.
the days longer.
Yeah. Yeah, so right. Yeah. Sun rises later and sets later. Yeah, during summer. So that's what we're all about to do here. All right, so yeah, let's get the ball rolling on thermodynamics. Got some posters, got some demos for you guys. But so how do you quantify how hot is something and why would something have a certain temperature? So there's this kinetic energy theory of temperature, which is if you look down at the molecular level, it has to do with how fast are atoms vibrating. Okay? So the faster they vibrate, that's going to correspond to more thermal energy, and then the thermometer would read a hotter temperature. Okay? So here, guys, I got these 3 temperature scales. And in this class, well, since we're doing metric system, we'll tend to be using these left 2, but since we're Americans, we also have this one on the right, called Fahrenheit. There's a whole history behind these, but here, just to show you guys how these compare. Okay, so what temperature does water freeze, like turn from a liquid to a solid? Yeah, okay, there you go. 0 degrees Celsius, and then in Fahrenheit, that's 32 degrees Fahrenheit. And then at sea level, and since we're in Florida, we're at sea level, what temperature does water boil? Yeah, 100 degrees Celsius, and then 212 degrees Fahrenheit. Now, historically, the first of these 3 systems to be developed was Fahrenheit, and then again, whole weird history I'm going to skip. And then Celsius came around, and okay, so that's nicer from a like in a metric sense. Okay, but then if you make the temperature colder, it turns out that there is such thing as a coldest temperature where maybe you can't make it any colder, the atoms effectively stop vibrating. Okay? It's called absolute zero. Okay. And in the Celsius scale that corresponds to negative 273 degrees Celsius, it's like negative 273.15 something. Okay? Uh, so there's this third system that was developed called Kelvin, and it actually starts 0 Kelvin at absolute zero, right? Which is actually what you need. Do you guys remember that? Ooh, do I have this here? Oh, here it is. Here it is. Okay. Do you guys remember? We briefly talked about ideal gas law a couple weeks ago. You guys remember this ideal gas law? Okay. Hey, this T right here. Like, if you want to scale up temperature like double or triple the temperature, you have to use an absolute scale, which right here is only this Kelvin scale. Right? So that would go there. Right? Right. So how about the conversions? How do you convert from one to another? So here I have two conversion formulas for you guys. Okay. From Celsius to Kelvin, you very simply add 273. Anyway, just chop off this 0.15. Don't worry about this much. Right? Which means that these are actually scaled the same. But like a change, guys, see if you guys are following this equation. Is a change in 1 degree Celsius the same thing as a change in 1 Kelvin? Is that the same? Temperature change? Yeah, the change is the same. The change is the same. Okay. Actually, you can see it right here. It's to go from freezing to boiling in water, that takes 100 degrees Celsius. But how many Kelvin does that take? What's the change here? Guys, what's 373 minus 273? That's also a change of 100, isn't it? Yeah. So the change is the same, but it's just shifted by 273. Right? Now, to go from Celsius to Fahrenheit or vice versa, okay, you also need a factor. Uh, 9/5 is approximately 2, so you can kind of round it. Sometimes you could say like times 2 plus 30, you get it fairly close. Okay? So, guys, what if you go vacationing over in Europe this summer, and they say, oh, it's 22 degrees outside. Yeah, in the States, that would mean it's freezing, but over in Europe, that means something totally different because they're talking about Celsius, not Fahrenheit. So what you can do, here, I'll show you guys here. If I take 22 degrees Celsius, and I say times 9 this, and then plus 32. Okay. So for Americans, that would be about 72 degrees Fahrenheit. You see that? Okay. Or if you want to say, take that 22 degrees times 2 plus 30, that should be pretty close. Yeah, that'll give you a rough idea. Okay, so about room temperature there. Okay. All right, let's look at laws of thermodynamics. Laws of thermo. So there's this zeroth law of thermo says if two systems are in thermal equilibrium with a third system, then they're in thermal equilibrium with each other. Okay? It's thermal equilibrium. You can think of that as two objects have the same temperature. And if they have the same temperature, there's no impetus for a transfer of thermal energy. So say I got these three objects right here. Now, right now, all these three objects are the same temperature as the room we're sitting in right now. So if I put these next to each other, there's going to be no transfer of thermal energy because they're all the same temperature. So that's kind of what this one does. Right? The first law of thermodynamics is actually related to one that you guys learned last semester. Do you guys remember conservation of energy? Now, last semester we worked with mechanical energy, but now we have a new form of energy, which is thermal energy, and I have an equation that goes with it too. Right? But it's effectively conservation of energy. So energy locked by one system, gained by another. You cannot destroy or create energy. Right? You can quantify it and transfer it, and it can change forms, but it can't change quantity. Right? Now, the second law of thermo, guys, look here. This one's a lot more abstract, right? So it jumps way up in abstraction here. There's this property in thermodynamics called entropy. Entropy. You guys see this word entropy? Right? And sometimes it's said to be like analogous to disorder, but there's a way you can quantify this too with an equation. Okay? And as these thermodynamic processes are happening, like if there's a heat transfer from, say, one object to another object, like if I made this hot and this cold and put them next to each other and there was a heat transfer, right? That process is not really reversible, right? Like, here, guys, look up here. What do you guys think about this? Is what if this object was really hot and this object was really cold? Let's say like, here, I'll throw some numbers on it. Give you guys some numbers to look at. Is what if this object on the left was like at, oh, let me look ahead a little bit here. I know yeah, let's call this 30 degrees Celsius. 30 degrees Celsius. Let's say this object on the right is at 10 degrees Celsius. Right, you guys see that? 30 versus 10. Okay. Now, if I left them here for like a couple of hours, and let's say they were isolated, so I put them like in a styrofoam box. Right? Do you guys think after a couple of hours, what would be the final temperature of both of these objects? And they're the same mass, same material. Do you think it'd be 20 degrees and 20 degrees? Do you think it'd be like that? Right. Or sometimes I'll say you have two aquariums so full of water and you like mix the water. Okay. So it looks like something hot and something cold can form something that's like a middle temperature, right? Spontaneously. So this top picture can turn into this bottom picture spontaneously. But guys, can you ever spontaneously expect the reverse to happen? Like if I left these two at the same temperature, actually these right now are the same temperature as each other, right here. Boom, boom. Okay. Which could I walk away and come back an hour later and one has spontaneously picked up energy from the other, so now one's really hot and one's really cold? Guys, is that ever gonna happen? Here, guys, what did I just ask you? What did I just ask? Does anybody know the question I asked? Does anybody hear me talking? Guys, what question did I just ask you? I'm asking you something really, really deep and abstract here. You have to think really deeply about this. Okay, here, I'm going to backtrack about a minute ago. Okay, so I said if this object was hot and this object was cold, has these numbers, and I left them, let's say, oscillated in a styrofoam box, there's going to be heat transfer, right? And they'll eventually reach an equilibrium, like 2020. Okay? But what if they start out at the same temperature, which, by the way, they are right now, and I walk away and come back later? Is this guy going to spontaneously pick up a bunch of thermal from this and suddenly become really hot? This guy becomes really cold. Would that ever happen?
No.
Not spontaneously. Now you can force it to happen with refrigeration, but that would be an energy-intensive process. Okay? So that is all embedded in this second law of thermo. It talks about the like the spontaneous order of thermal processes to happen. Like, now this third law, I don't think we're ever going to touch very much in this class. It just says entropy approaches a constant values, temperature approaches absolute zero. So don't worry about that. That one's much. Okay. All right. But just to recap here, the first law you effectively know from last semester, and the second law has to do with like time order process, like spontaneous processes. Right. And more on that later. I got some equations stuff, you guys. All right, let's talk about forms of heat transfer. You guys may have learned these, I don't know, middle school, elementary school. Here, guys, if I cover these up, what's one form of heat transfer? There's three. What's one of them? You guys probably know these from the past.
Friction?
Oh, okay. If there's friction, that might be one of these. You have to have what?
Motion?
How about direct contact? So conduction. So direct contact. So here I got this pot of boiling water. Guys, what if the pot's all metal and I touch this metal handle? Does that feel hot? Yeah, because I touched it directly. That's called conduction. Right? So the heat can transfer by direct contact. Right? What's another form of heat transfer?
Like indirect contact?
Right, here, guys, I'm pointing to this fluid down here, this water. Okay. Guys, what if the bottom of the water is really hot and the top water is cold? Is the water going to start to spontaneously move and mix because there's a temperature differential?
Yeah.
It sure will. And what's that called? Also starts with a C. Convection. Okay. So it's bulk movement of fluids. How about the Gulf Stream that's moving water around in the Gulf and the Atlantic Ocean? Right. Part of that process is convection. Right. You have warm water in the equator and cold near the poles. Right. So that's part of the process. Right. And how about what's this last one I'm covering up? Starts with an R. How about if you have the stove range, right? And you put your hand near it. You don't touch it. Don't touch the stove range. Huh? Radiation. There you go. There's heat energy that's radiating, right? So you put like 2 inches away, you're like, ooh, that's really warm, right? It's radiating. And this, guys, which of these three do you think is the only one that can travel through the vacuum of space?
Radiation?
Yeah, this one here. Right? So like, how does sunlight get to Earth? Okay, that's electromagnetic waves, isn't it? Yeah, it's called radiation. All right, so you got that. Okay. All right, efficiency here. So any process you run, let's say you put in some fuel to an engine and you run the engine, it's never going to be 100% efficient. So you put some work in or some energy in, and there's going to be some useful work out, but then there's going to be some waste heat. Right? You take this ratio, useful work out compared to total work in. It's called efficiency. There's some other equations for it too. Right? So if you put a gallon of gasoline in your car, there's energy stored in those gasoline molecules, like chemical energy. And making the car go is mechanical energy. And your car might be, about 30% efficient. So that's to say it takes about 30% of the energy from the gasoline and turns it into motion of the car. Okay. All right. So entropy. I got a picture. Now this is kind of an analogous example. I mean, it is related. Okay, so suppose here I'll tell you guys the story because it's related to what's actually going down at the molecular level. suppose you go to the beach and you construct a sandcastle. Now that took effort on your part, right, to construct a sandcastle. Now isn't that sand like highly ordered, right? Or what if you put some marbles in a jar and you carefully like sorted them like red versus green, okay? But then guys, you come back the next day, has the waves and the wind all blown the sandcastle down. Now it's like a random pile of sand, right? Or you mix up the bag of marbles and now they're all like all scattered and ordered, right? Now you could expect spontaneously to go from the pictures on the left to the pictures on the right, couldn't you? Right? But would you ever expect there to be a random pile of sand? You come back the next day and it spontaneously turns into a nicely ordered sandcastle, right? Or you mix up a bag of marbles and you pour them out and they're like, oh, zoop, they're all neatly ordered, right? That'll never happen, right? So it's a spontaneous order of process to happen, right? Now, when you bring in a transfer of thermal energy, it's the same thing, right? Again, why does something hot next to something cold reach an equilibrium temperature, right? And it's related to this, right? There's a order of spontaneous processes, right? So there's more ways for things to be disordered than ordered, right? And we're going to run this equation. I think it's next. Yeah. Okay. So this big picture here. I just want you guys to look at this and kind of digest this from a forest for the trees point of view. Okay. So what I'm telling you guys is that the change in entropy is the transfer of energy divided by the absolute temperature that's happening at. Right, you guys? Okay. Okay. But actually, I'm saying you're okay with that, but that's really weird. I think that anybody even figured that out. I think they figured that out about 150 years ago. I think something like that. Right, something like that. Right. So let's learn this example with the same numbers that I was using before. I have a 30 degrees Celsius next to a 10 degrees Celsius block. And let's say there's a transfer of thermal energy of 100 kilojoules, whatever mass and material they're made out of, right? So that they eventually reach this equilibrium of 20 degrees Celsius. Is that okay? Okay. Now, what happens to the entropy in the system playing off this box in equation here? Well, let's run the numbers. So there's a change in entropy for the red block, and there's a change in entropy for the blue block. Right? I guess the hot cooling down and the cold warming up. Okay. So the hot block is losing 100 kilojoules, and the cold block is gaining those 100 kilojoules. Okay. So there's conservation of energy. So that's the first law. That's okay, right? Energy is conserved. Okay. Now this 25 degrees Celsius right here, that's the average of 30 and 20. So this is not exact, but it's close enough to work. Right. It's like the average temperature of this hot block cooling down was 25 over the process. Okay. And the average temperature of the cold block warming up was 15 degrees Celsius over the process. Okay. But remember, I don't want to run Celsius in any of these equations because that's a relative scale. They can go negative, right? I need an absolute value. So I'm going to do plus 273 to turn this into Kelvin. And it looks like the change in entropy for the hot block. Here, guys, look at this. Guys, think really deeply about this. This number gets really weird. Right? This is a class that I took in college. There was a whole, what I'm covering today and probably for the next few days, I took a whole semester class in college and this like really hurt my brain while I was taking this. Right? So the hot block cooling down effectively loses 336 joules per Kelvin worth of entropy. Okay? And the cool block warming up gains 347 joules per Kelvin worth of energy. You guys see that? Okay? If you run these fractions, that all leads back to this, and the temperature changes. Okay? Now, if you look at the end results for each individual block, and you add those together, which I did right down here, the 3 plus 347 for the cool block warming up, and the minus 336 joules per Kelvin for the hot block cooling down, there is a non-zero difference. Okay? You guys see a positive difference from that? Okay? In fact, I could make these numbers whatever I want, and because of how fractions work, this difference will always be positive. Always be positive. Okay? And that actually is the second law of thermo. Let me go back and reread that. As time moves forward, processes tend to move toward less usable energy and toward more disorder. Entropy always increases in the universe. In the universe. Now, in the universe is kind of key too, because notice that one of these blocks, the entropy actually decreased, right? But the other one it increased, but overall in the universe, or like the sum total, entropy always increases, right? So again, the hot next to the cold will reach an equilibrium spontaneously, but it will never happen in reverse spontaneously. Right? Like that. All right. What are we doing here? Well, I got some more slides for you guys, but there's also some demos I wanted to do. So I'm going to kind of skip ahead here. Here, let's do a thermal engine here. All right, so here I have a Stirling engine. It's one of my slides, and here I got some pictures on this too. Okay. All right, so I'm going to put some hot water underneath this. It's going to heat up the bottom. It's going to cause this air to want to expand. Once it heats the bottom plate, the air is going to expand. Okay. Once the air expands, causes this mechanical motion. And notice this this diaphragm looking piece is going to move up, and that's going to that increased volume causes the temperature to go down a little bit, and then there's the cyclical process. Okay, all right, so let's try this out here. I got some water heating up over here. I pour in this water. All right, got some really hot water right here. Hot water, hot water. Okay. All right, set this right here. Okay. Now sometimes this takes a few seconds to heat up. Okay. So what's happening right now is I'm waiting for the bottom middle plate to heat up because the water's sitting right underneath it. Okay. And now see there, guys, there's a temperature differential because this hot water down here is much higher temperature than the air in this room. So there's thermal energy that's traveling. Okay, you guys saw there was a cup full of hot water down underneath this thing, right? Okay. There's thermal energy that's trying to travel from the hot water, like up through the Stirling engine and into the room to reach an equilibrium temperature, kind of like those two blocks you guys were just looking at. And if I give this a little spin, oh yeah, that's plenty ready to go. Yeah, that'll just, look at that, guys, I just gave it a little tap and it's just spinning. Hey guys, how long will it spin for?
For a little while before it runs out of energy.
Yeah, there you go. Right, until it runs out of the thermal energy. Okay, because the water down here in this cup, right now is really hot, but of course that's not going to last for probably more like 10 or 15 minutes. Right, because eventually it cools down enough and reaches something closer to room temperature. Like that. All right. Let me find some demos for you guys. Here, actually, here I'll have Bill Nye explain what you guys are looking at right there. Got some other things.
Let's say this beaker full of very warm water is a source of.
No, sorry guys. Where's my volume? I don't know.
Let's say this beaker full of very warm water is a source of heat. Here's a special type of engine, a Stirling engine named after the Stirling brothers who invented it, got a patent in 1807. The heat from this water is warming the bottom plate of this engine. Give it a little nudge. The engine will run. Now notice there are two pistons. There's this little one up here, the primary, and then there's this big one down here, the secondary. And as the heat from this water warms the bottom plate, it makes the air expand. The expanding air drives the piston. So this is a way to convert the energy of heat into what we call mechanical work, or making something spin. And the extraordinary thing about Stirling engines is they're so efficient. It's just a little bit of hot water. And look how fast it's making the wheel go. Now watch what happens when we take the same Stirling engine running clockwise and put it on another beaker, but this one's full of ice water. In just a few seconds, the Stirling engine will slow down because it's lost its source of heat from the bottom. But now it will run the other way from the ice. So there's an old joke in science. A thermos bottle keeps cold things cold and hot things hot. How does it know? Well, the reason it knows is because, in a sense, in science, there's no such thing as cold. There's only the absence of heat. So this is still a heat engine, and it's running off of heat. But the source of heat now is the room. The air in this room is warming the top plate, and heat is now flowing down through the engine instead of up through the engine as it was over on the source of hot water. Now, Stirling engines have been proposed for all sorts of things. In the early 1800s, they were used to pump water all over the place. People have talked about putting them in cars again. But the tricky thing about a Stirling engine, they're hard to speed up and slow down. The great thing about a car engine is you can speed up and slow down very easily. You've probably heard of a diesel engine. That's named after a guy named Diesel who invented the process. Then your car that runs off gasoline has the Otto engine, O-T-T-O, another German scientist. There's all sorts of heat engines. There's the Watt engine, the Rankine engine, the Brayton engine, the Atkinson engine. And they're all different arrangements of pistons and valves to convert heat into mechanical work. It could be that the Stirling engine is going to make a big comeback because it's so efficient. And maybe you'll be the scientist or engineer who finds a way to use it in extremely important application.
All right, so for the rest of class today, here, just got a few polyhedrons for you guys. And this will end the week right here. A few polyhedrons.
Browning in motion. You guys be reading about what Robert Brown did back in 1830. He's looking in a microscope. And in the microscope, he sees little things jiggling. And at first he thought it was something in there alive. There's little particles of soot. And these little things are jiggling, jiggling, jiggling. And Brown thought that maybe he saw atoms. But they weren't atoms. Guess what they were again? Little specks of dust banged into by, guess what? Atoms. It's like this. See this styrofoam cup? You guys can all see this. See this little BB right here? Little BB in my hand? I got a whole bunch of them there, see them? Spill them on the table. See all those BBs? You guys can't see those BBs because you're too far away from them, okay? But can you picture this? Can you picture the styrofoam cup on the table and all these BBs all moving around haphazardly, chaotically, and every once in a while the BBs, more BBs hit one side of the cup than the other? What would the cup do? Wouldn't the cup start to jiggle? And you guys can see the cup, but you can't see what's making the cup jiggle. You know that something smaller than you can see is making the cup jiggle. And that's what Robert Brown saw in his microscope. He saw little particles big enough to see jiggle. Why jiggling? Small enough. There could be more atoms on one side than the other. A little bit more net force on one side of the other. Boom, that thing will jiggle around. So in response to the jiggling atoms, boom, the visible observation, microscopic particles moving, gravity in motion. So any one person's one breath. You guys got atoms from that breath right now. Now, usually people take more than one breath. Leonardo da Vinci, an old dude, took many, many breaths. In all his breaths, you have hundreds of billions of atoms of Leonardo da Vinci's breath in you or any other person who lived for a long time. So you were made up of the atoms of everyone who was ever before you. How many people in the world today? About 4.5 billion. That's 4.5 times 10 to the 9. How many people compared to how many atoms in your lungs? Which is bigger? You know, there's a lot of people. People at 10 to the 9. Atoms at 10 to the 22. How many people have been on the planet since the beginning? Nobody knows. But Arthur C. Clarke has made an estimation, and he said it this way: behind every human being stands 30 ghosts. That 1/30 of the whole human race from way back is walking the earth today. That number's changing quickly. Let's say 1/30. So that means there are 30 more people on the earth from time zero than there are now. Now there's about 4 billion. And there's 30 times that number for the total number of people that ever lived. 3 4s of 12. Call this 100. That's like 10 to the 11th. 10 to the 11th is 100 billion. So 100 billion people in the world. But the number of atoms in your lungs, 10 to the 22, what's that? Billion, 18. 10,000 billion atoms in your lungs. So many, many, many more atoms in your lungs than people that ever lived. So you can be rest assured that inside your lungs or inside your body at any moment are atoms from every human being who ever lived. Hey, let's talk about this expansion and this expansion under different temperatures and everything. We got something here that's kind of neat today. Ted, could you give me a hand? Talk about low temperatures. Ted's brought over here some liquid nitrogen. This liquid nitrogen is about 190 degrees below 0 Celsius. Really, really cold. almost 80 degrees above the absolute zero temperature. Now, can we have a volunteer jam their hand in there for about 5 minutes? Okay, nobody gonna do that, right? Okay, let's show how the let's show how the volume of something will change. Here's an air-filled balloon, gang. Okay, what's going to happen to the volume when it gets cold? How many say, oh, it's going to expand? Stand up. And what happens to the volume, gang? Look at that. Now it's going to start to warm up to air temperature. What happened to the volume? What happened to the volume? We bring it above air temperature? Bring it a little closer, Ted. Yeah. Let's try the flour. This is a flour Ted found out in the ground. It's kind of nice and limp, right? Kind of limp, isn't it? Okay. What happens if we slow those molecules down? Yeah, why did it fizzle like that? What's going on? Oh, gang, did you see such a thing? See, right now, it goes through. With a little effort, it goes through, yeah? I'm not going to take the time to heat up the ball. I'd waste your time because you know the ball would get bigger and no way it would go through. I'm going to heat instead the ring. You get that ring nice and hot. Is the ring expanding? Yeah, it's expanding. How about the hole? Is the hole expanding? See, a lot of people think this. A lot of people reason that the hole is it's gonna expand this way and expand in this way because the ring is gonna get fatter. Will that ring get fatter? Turns out it will. So they think this part will expand out here, and this part in here, and the hole gets smaller. But lo and behold, it's appreciably bigger. So the hole does get bigger again. If we take our ring, and we cut it up into 4 pieces, gang. 4 pieces. And if I put any one of those pieces in the oven, would it get bigger? Yeah. Would it expand and maybe look like this? No way. It's going to expand and look like that. And this side here is longer in an expanded state than like this. So take them apart and look at it and you can kind of see it. Or take your ring and open it up like this. Is it going to get fatter? Yes, it's going to get fatter. So it expands out to here maybe. Out to here maybe, yeah? But that's not the end of the story. You see, we're so busy thinking about what happens like this, huh? That we forget it's expanding this way too. And it expands lengthwise as well. And lengthwise, we see it expands out to here. And I submit to you that this dotted line on the top is longer than the solid line below. And that dotted line on the top represents the new inner circumference. So every part of the ring, the thickness, the width, circumference, outer, inner, everything expands by the same rate if the heating is uniform. And it pretty well was here. So the hole gets larger, okay? You've got a jar of peanut butter, you can't open it up. You give it to a muscle-bound type, still can't open it up. So what do? And it's handed to you. You take it over, put it in the stove upside down momentarily, or put it under the hot water. Doesn't that metal lid expand? Does that make it tighter against the glass or looser? Looser. And hey, mind. Hey, bronze, one thing, wonderful, but the mind too. So you think, and you can open it up by just heating it up. Turns out the whole darn thing will expand, whole and all. Hi, gang. Thermal expansion time. Here I have what's called the bimetallic strip. It's a strip of metal consisting of 2 kinds. Brass on one side, steel on the other, welded together. I'm going to heat it up. Looks like it's bending. It's bending because one side's expanding more than the other. If I take this and turn it into a coil,
and heat it up, it would shrink. Or cool it, it would expand. That would be a thermostat.